Hi, everybody. Uh, the topics here shown in gray, we covered those in the previous videos. So today we're going to start with the first video on the TCA cycle. So these are the topics we're going to cover. Let me again move here myself. Okay. So this video will just cover a brief overview of the cycle. Then we have the gateway reaction, the pyruvate dehydrogenase reaction that we'll spend quite a bit of time in it. And then the reactions that deal with the two carbons that are coming in, the two carbons that are coming out, how we return to where we started in the cell cycle, how we make up intermediates that get used for other purposes, and finally, how the TCA cycle is regulated. So where are we in our big fundamental organizing scheme of all of metabolism? So we are right here. We're going to completely break down whatever we got from glycolysis. That was a pyruvate. That's going to go all the way down to carbon dioxide, CO2. And so it's going to be completely oxidized, which means, so pyruvate will be completely oxidized, which means that we're going to get some electrons out. Something's going to get reduced. Of course, that something will be NAD+. So all these electrons will become NADH. So right here, you see a major product of the TCA cycle is actually NADH. So this is where the TCA cycle fits into our general scheme. How does it look like? Well, we got 3 carbons from glucose, and now we are not dealing with fermentation here. So the TCA cycle and respiration that will follow is what comes after glycolysis, but without invoking fermentation here, right? So we're not dealing with any lactate or ethanol in this at this juncture here. So we begin with pyruvate, which we got from glycolysis. It's going to lose 1 carbon, and it's going to get oxidized too. And then 1 carbon is going to leave as CO2, and that will become acetyl-CoA. So that's the acetyl-CoA is a very common and fundamental metabolite in the cells. It's sort of an activated form of a 2-carbon unit. This is actually the carbon that's going to enter the TCA cycle. So 2 carbons. So you start with 3, we have 2, and the 2 carbons will enter the TCA cycle in the form of acetyl-CoA. And then the way it's going to happen is the 2 carbons will join with oxaloacetate, which is a 4-carbon unit. So 4 plus 2 will give you a 6-carbon unit. That's citrate. It's going to rearrange for reasons that will become apparent to another 6-carbon unit, and then 1 carbon will be lost. Not the same carbon that entered in, okay? So the carbons that come in and the carbons that come out are not necessarily the same. So we have 6 minus 1, that's a 5-carbon unit. We lose 1 more, okay? And then we have 4 carbon units. So already we will see what came in, what came out, and the rest of the cycle is actually to go back to a 4-carbon oxaloacetate and repeat again and again and again. So the 2 carbons are coming in here, and one at a time are coming off at these points. Okay, so this is the gateway, and this is how they come out. So in the end, it's carbon neutral, the whole cycle. Okay, it stays at 4 carbons. Now, why do we do it? So a key, as I already said, a key product of the TCA cycle is electrons. Okay, these electrons will get fed into the electron transport chain, and eventually they will find their way onto oxygen or other acceptors. And that is the way that cells, all cells, charge their batteries. We call them mitochondria in our case. Bacteria is the same thing. And then they can make ATP. Okay? So electrons, here we see where they come off, okay, in the TCA cycle. The other main reason, much like glycolysis, many of the TCA cycle intermediates are key building blocks for a lot of biosynthesis. Pyruvate, we have already seen, that's a glycolytic intermediate as well. So it makes, or glycolytic product, it's a precursor for amino acids, alanine, leucine, valine. Acetyl-CoA, you can make pretty much all the lipids and fatty acids. And a very important building block is alpha ketoglutarate or 2-ketoglutarate. That's a 5-carbon unit. It's a very unusual one. It's, if you want to build things, imagine Legos here, and this is the kind of rare and special Lego piece that you need, but it doesn't come in, it's not very abundant. So 2-ketoglutarate is very important. It makes amino acids. It's also used to make nucleotides, purines in this case. Succinyl-CoA is, of course, a 4-carbon unit that's also activated because it's bound to coenzyme A. So it has it's a high energy compound, 4-carbon unit, and it's used to make porphyrins. Porphyrins are the building blocks to make hemes, oxygen carriers, things of this nature. And then we come to a couple 4-carbon versions, the fumarate and oxaloacetate, and it turns out that they are also key intermediates for a variety of amino acids and the other class of nucleotides, the pyrimidines. So the ones that contain pyrimidine bases. So very important building blocks come off the TCA cycle. So now we already have 2 reasons for the TCA cycle. One is electrons, the other one is building blocks. The third reason, why is it even a cycle to begin with, is because if things keep going around in the merry-go-round here, I mean, you don't need to keep the intermediates, these compounds, in high amounts. So it's sort of an efficient way to keep the reactions going by keeping the intermediates at a low concentration. Okay. It doesn't necessarily mean that, chemically speaking, for electrons and building blocks, it has to be a cycle. It's just a more efficient way of doing it. Who discovered it? I mean, another name for the TCA cycle, which stands for tricarboxylic acid cycle, because some of these have 3, like citrate, for example, have 3 carboxyl groups. The other name is, of course, the Krebs cycle from the person who discovered it, Hans Krebs. He got the Nobel Prize for it in 1953. And it's an interesting story, how when he first proposed that there is a cycle, he submitted the manuscript for publication to a very prestigious journal, Nature, and was rejected. And, it's not a pleasant position to be as an editor of a journal when you reject something that will become Nobel Prize worthy. But it was, and that was the letter that Krebs received from the journal. It was not rejected for any particular, flaw. He was widely respected, Krebs was, and it was just they didn't have space for his paper. All right, so where does it happen in our cells or in all of eukaryotic cells? It happens inside mitochondria, okay, which look something like this. And it's a membrane-bound organelle, actually has 2 membranes, okay, the inner and the outer membrane. And the TCA cycle is taking place in the deep inside the mitochondria, in the inner, behind the inner membrane, in the matrix. So this is where it's happening, okay? And remember now, glycolysis was happening in the cytoplasm, okay? It's a very ancient pathway. We said we can get it in vitro, even in test tube. That was the whole point, how you can reconstitute fermentation from in vitro extracts. So the problem here is that glycolysis is in the cytoplasm. This is where pyruvate is made, okay? And I just told you that the TCA cycle, including the first reaction, the pyruvate dehydrogenase, happens inside the matrix, okay? And nothing can go through the inner membrane, okay? It's practically impermeable unless you have specific transport systems. So the problem is, how do you get how do you have the product of glycolysis entering inside the mitochondria? So that problem will be solved in the next reaction. We're going to talk in the next video, the gateway reaction of pyruvate dehydrogenase. So until then, enjoy this video about the overview of the TCA cycle.